Hey guys, today we're going to be completing, or mostly completing, the 1300 watt off-grid power system behind me here. And you saw me setting up parts of this system in previous videos, in particular the SOK battery rack that is directly behind me. In this video, we'll be focusing on the inverter connections. I have a pair of MPP Solar LV6548 inverters. They are 6,500 watts each. So we're going to set up the battery wiring, the AC wiring, and have these operating in split phase mode. That means it will output both 120 and 240 volts, which is the standard here in North America in the United States. And when we do start getting into the AC wiring, I like to always, make a note that if you have any questions or don't know what you're doing, you should not be attempting this and you should contact an electrician. All right, so I've got my two LV6548 inverters here from MPP Solar. I've got both of the front panels removed from each inverter. This is needed to access both the terminals for the battery, AC, and for the mounting holes on each inverter. And I'll be mounting them up on this temporary wall structure here. This is 5/8 plywood, I think, and then I have it covered with 1/4 inch of cement board the whole way around. Now the use of the cement board is per the user's manual, where it says it's suitable only to be mounted on non-combustible surface. That means you're not supposed to mount this inverter directly to wood. Additionally, they have some spacing requirements here. They want 50 centimeters above and below the inverter and 20 centimeters to the left and right of the inverter. Now I do have limited space here, and this is a temporary test setup, so we're going to squeeze them a little bit tighter here. So the top of the inverter has a couple of tabs here. You can see the teardrop style holes. I'm not sure what they're actually called. So I've already measured and installed a couple of screws where I want these inverters to sit. I simply need to lift them on the wall at this point. So on the bottom of these inverters, there's a mounting hole on the bottom right, and there's another mounting hole by the charge controller down here on the bottom left. So I always drill these holes out with a very small drill bit first to start a pilot hole. For the AC connections on these inverters, I'll be using this 70 amp Homeline Square D load center. So we've got terminals for line 1, line 2, and then the neutral, and then I also have a ground bar installed up here. And I'm going to situate that load center right between the two inverters here near the bottom. So I've got two different types of fuse blocks here, and I've also got a set of bus bars. These are Class T fuses. They are HRC, or high rupture capacity. So these fuse blocks here are actually the style that I prefer. I purchased these a couple of years ago from the Alt-E store. And basically you get this fuse holder that comes with these very heavy bars, and then you get a fuse with it. And the fuses I purchased with mine are JLLN 110 amp. And I use these fuse blocks in my battery shed currently for my EVE 230 and 280 amp hour batteries. So the problem with these is they appear to have been discontinued. Alt-E doesn't sell these anymore. They do have one or two that look similar, but they only have one choice in fuse. So I found on Amazon these fuse blocks, which have the size fuse I want. And this is actually the exact same mounting plastic, but they have a different terminal on here. And originally I was just going to take these fuses out of this holder and put them in these other holders that I like. But I'm actually going to give these a try because these terminals actually look pretty good, and they look like they're designed such that you do not need to use a ferrule on fine strand wire. So we're going to give these a try, and I selected 200 amp for this project. So to get to that fuse size, I have 6,500 watts divided by 48 volts. This is the nominal voltage, so it will go a little bit lower than this at the end of state of charge. But we're going to use this for the calculation. And then in overcurrent devices, we typically derate to 80% for a continuous load. So I'm going to multiply by 1.25. So that gives us a fuse size of 169 amps. And then we'll round up to the most commonly available size of 200 amps for this use case. And then I'll be using this pair of bus bars to connect the battery terminals to both of the inverters. So as you can see, these came from Current Connected. These are brass, I believe. I think they told me these are brass. I do like them, but I also feel like they could be made a little bit better in terms of the thickness of the bus bar and the quality of plastic they used for support. I'm going to mount one fuse block below each inverter here, and I'm going to use this on the positive. Now, it would be nice to actually use a circuit breaker instead of a fuse for this purpose. However, I'm having trouble finding actual circuit breakers that will work with the amount of current this inverter consumes. I've seen some people use those Blue Sea systems, the cheap flippy type breakers, and those say they're rated for 48 volts, but to my knowledge, per a question I asked directly to Blue Sea systems, those fuses cannot support up to 60 volts, which is required by these inverters. So my understanding is that those are hard limited to 48 volts. Some people are using them, some people seem to be fine using them, but when the company told me they don't go up to 60 volts, I didn't want to use them. So on the leftmost inverter, I have the fuse block mounted in the same location. We're going to use this again for the positive lead of this inverter. And then I'm going to mount my bus bar, distribution bar, whatever you want to call them, positive on the right side of the fuse block, and I'll put the negative on the left side of the fuse block. Now, to run the AC output from this inverter down to this breaker panel, I'm going to use a piece of 3/4 inch EMT conduit. I mean, I guess EMT is technically tubing, not conduit, but I was going to use this liquid tight flexible conduit that I had from a previous project. However, the fittings for this are actually quite expensive, so I opted for the EMT, and my conduit bending skills are pretty good, but they're not perfect yet, so that's why it does look a little odd. Now, the holes in the bottom of this inverter are actually quite large. You can see how large they are in comparison to this conduit piece. So the hardware store sells these little adapter plates. This is a 1 inch to a 3/4 inch adapter. So I'm going to place one of these on the bottom of the conduit fitting. And then a second one of these goes on the top of the conduit fitting. And then I've got these little plastic bushings here which sit on top of the conduit fitting, and they just provide a smooth surface to pull your wire through. Alright, so we're looking pretty good. We are ready to start talking about the cabling. So for the connection points on the inverter side of the bus bar, I'll be using some 1/0 gauge battery cable here. The instruction manual does recommend using 2-watt gauge, but from what I was reading online, 1/0 gauge should be perfectly fine for the required current. The bolts on the bus bars will require a 3/8 inch diameter lug terminal, and the studs on the inverter will require a 5/16 inch diameter lug terminal. So for making the connections on the fuse block, we've got an 8mm hex bolt, or Allen head, however you want to call it. And then we've got a 17mm nut on the bus bar. So I'm just going to insert the stranded wire directly into the fuse block. The other end will go on the positive bus bar. Then we've got a flat washer, a lock washer, and the 17mm nut. On the inverter side, the left side is the positive, the right side is the negative. This is the newer of the two inverters I purchased, and I do like that they've color coded them, so they now have a red marker here and a black marker over here. Positive on the positive terminal. And these inverters came with some pretty nice serrated flange nuts here, and you will need a 13mm socket to tighten that down. So on the right hand side, the fuse block is connected to the inverter the same way, and then we have a long positive conductor that comes down and goes over to the bus bar on the left hand side. And we're going to wire the negative connection up to the inverter the same way. The only difference is we'll just go straight from the bus bar to the inverter. We won't have a fuse block on the negative conductor. So I found that these 1/2 inch conduit straps here are perfect for tying down this cable and making it look nice and neat and tidy. Additionally, these fuse blocks come with some very nice protective covers here for safety. So you simply squeeze them in, and there are tabs that grab onto both sides. For the AC wiring, I'm going to be using this number 6 gauge THHN. This is standard wiring you'd put in an electrical conduit. Now the manual for this inverter does recommend 4 gauge. However, number 6 THHN in an EMT conduit is more than sufficient for the amount of power this inverter is going to be putting out. Additionally, I don't think there's any way you're going to get 4 gauge wiring on these terminals. I've not personally tried it, however, this number 6 seems to take up almost the entire area of this terminal. So I have black for leg 1, red for leg 2, and then white is for the neutral, of course. Underneath this inverter, you'll see the connectors are labeled L, N, and ground. L is line, or the hot lead, N is neutral, or the white lead. And then of course ground is going to be the green lead. Now with this wire here, you see it's not round anymore. I've sort of squeezed out the strands a little bit, And my goal is to, try to flatten it just a little bit, make it a little bit rectangular shape. These terminals are actually not very good on these inverters. So if you put a round wire in there and then you tighten this down, the clamp that tightens down is going to apply force in only one location of this wire if it's round, whereas if you've got it a little bit flat, it's spreading that force over a greater area. And the reason why that's important is these clamps actually break very easily. And you can see over here, I actually did break one of them. The clamp part just snapped right off. Really, I wish they would just let the leads come through here, and then you can use like a wire nut or a Wago connector or something. But so the black wire is going in the terminal for the output marked L for line. So on the electrical panel, we have one lug for line 1 and one lug for line 2. So I'll just put the black wire on the first terminal to the left. And next we'll run the neutral the same way. Alright, so this neutral bar on the top here does have a main lug where you would typically connect the main neutral. However, since we have two inverters, we're going to have two neutral wires coming in, and you cannot put two wires on one of these main lugs. I mean, technically you can, but I'm pretty sure that's against code. So for the ground conductor, I'll be using this number 6 THHN. Both of these ground conductors are going over to the separate ground bar here on the right. Now you'll notice I have a jumper going from the ground down to the neutral bar. And this is very important because this is where my setup is probably going to differ from most other people. So by default, these inverters come with a ground neutral bond in each inverter that is engaged when the inverter is operating in off-grid mode. Per the approval of MPP Solar, I have removed that bonding screw in each of my inverters. And I've done that because I want a ground neutral bond in the panel. You can only have the ground and neutral bonded in one location in your electrical system. These inverters will never ever be connected to the grid. They are only in off-grid mode. I have no AC input whatsoever connected. So if you ever consider connecting the AC input, you have not removed that screw, or you are wiring your system in a way such that you could have more than one ground neutral bond, you will not be doing this, and you will be keeping your ground bar separate. If you have any questions at all or don't understand the idea of ground neutral bonding, this is where I would strongly recommend you contact an electrician before you do anything. I've now double and triple checked all of the wiring, both the AC and the DC side of both of these inverters, the circuit breaker panel. I've checked the torque of all the bolts, so I'm ready to put my breaker panel on. You see, I've put a few breakers in here. I don't plan on using all of these breakers. However, since I've already punched out the knockouts in the cover plate, I want to make sure they're covered for safety purposes. And I'm also ready to put the front panels back on both of the inverters. So the last step in the wiring connections is to connect our batteries to our two inverter supply bus bars. So I've made sure that all of these circuit breakers are turned off on all four of these SOK batteries. They are all shut down. Going to be using some 4/0 cable for this connection. I've got a lengthy piece of red and I've got a shorter piece of black. No, these do not need to be the same length. So I'll have the negative come off the bottom right of the battery bank. And we're going to connect that to our negative bus bar. And with that connection completed, I've checked the torque of all the bolts on this bus bar. Ready to apply my safety cover. For the positive connection, I'm actually going to connect it to the top left. So we have the negative on the bottom right and the positive on the top left. And what that's going to do is basically help these inverters pull power from all of these batteries collectively. If I were to put the main positive and negative on the same battery down here, this bottom battery is going to be doing most of the work. So by making the second connection on the opposing end of the string of batteries, you can kind of see how it's pulling current through this entire battery rack. Just going to fish that off the top like so. So the positive has been connected to the positive bus bar the same way. And again, we're ready to put our cover back on. So we need to make one more connection to these inverters before we can turn them on for the first time. There are two types of communication cables you'll receive. We have the gray with a, I don't know, it looks like a VGA style connector. And then we have a two conductor red and black. And what these cables do is basically allow your inverters to communicate with one another. So this cable is for current sharing. We actually won't be using it here since we're not connecting any of these inverters in parallel. So all we have to connect are these two cables. And that can be seen in the user's manual here. One inverter in each phase. You see two inverters, P1 and P2. And then down here at the bottom, it shows you the two communication cables being connected between the inverter. And those will just connect here right behind where the conduit goes into the inverter. Alright, so now we're ready to start up our system. Current Connected has a very specific way they want you to start these batteries up to help avoid damaging the BMS and the components of the battery during the first inrush of power when you first connect your inverter. I've turned off all of the BMSs on all the batteries. To do that, I just pressed in on the reset button for a second or two and it shut all the BMSs down. Additionally, I have all 4 circuit breakers turned off. I'm going to flip one of the circuit breakers on. I'm then going to press in on the reset button of the top battery, and that will begin starting up the battery and will also engage the pre-charge circuit in the battery to pre-charge the capacitors of these inverters, which will avoid a large inrush of current if you were to just flip the circuit breaker with the BMS already turned on. And you heard it made a click noise. That was the current flowing and charging up those capacitors. And I see this is actually in the alarm state here, so perhaps we overloaded it somehow. I'm going to take a look at that. Alright, so that actually does appear. I guess that's how the pre-charge works. I don't know. It went into the alarm state, and I went in the analog info there, and it said SCP, or short circuit protection. I was going to grab the camera and get a clip of that. It clicked once more. It said 2 amps, and then it went back to SCP, and then it clicked a third time, and now it's in the run state. So I guess that is how it charges the capacitors up. That's a bit different than I would have expected. That's not how the EG4 batteries work. However, this does not have a pre-charge circuit in like the EG4 battery does. Now that we've confirmed this battery is started up correctly and is not in the alarm state, we're going to go ahead and turn on the remaining 3 batteries and allow those to start up individually. And now that those are started up, we're ready to try out the inverters. So I'm going to start up each one of these inverters, and then we need to tell it to operate in split phase mode. Go ahead and push the power button. And this one as well. Alright, so I do see there's a warning light flashing on this inverter. I haven't looked into it too much yet because we need to tell these inverters to communicate first, and that may be why it's complaining. So in the user's manual here, we can see setting number 28 is the AC output mode, and we need to go to the next page here where it says split phase. So for inverter 1 we need it set to 2P1, and inverter 2 we need it set to 2P2, or 180 degrees phase difference. Now you cannot change this setting while the inverter is on, so what I'm going to do is press the power button, which will turn it into standby mode, and you have a minute or two to change the setting before it shuts off completely. Okay, press and hold the enter button. We're looking for setting 28, and we need 2P1, enter, and then escape. Okay, and you see how fast that shut down there? And this one gets set to 2P2, 180 degrees difference. Oh, and you see I wasn't fast enough, so I'm going to have to do that again super quick here. Got it, 28, 180, 2P2. So now we're ready to turn both of these inverters on, and we want to double check that that setting has saved. Alright, so on the left inverter I see the top left says 2P1, and on the right inverter I see it says 2P2, so we know it saved our settings correctly. Alright, so now I've got my voltmeter up here. It is set to AC. I'm going to very carefully check this panel and make sure it's working as expected. So from neutral to black I should see 120. From neutral to red I should see 120. And from red to black, I should see 240. So those voltages are perfect. I'm now going to return my cover and never stick my hands in there again while this is turned on. Alright, so I want to check the idle consumption of these inverters. They are both running in split phase mode with no load on. So I've got my clamp meter on amps and I've got it zeroed out there. So I'm seeing approximately 2.2 amps, which is not too bad at all. That's roughly, what, 110, 120 watts. It's pretty good for 2 large inverters like this. So one last thing before we test out our inverters is we need to set the voltage parameters. Those will go into settings 26, the bulk charge voltage, 27, the float charge voltage, and then 29, the low voltage cutoff. So we don't have communication set up with this yet. We'll cover that in a separate video, I think. I'm actually having some firmware issues with this inverter. So I've used the values recommended by SOK, which is a bulk voltage of 57.8, a float voltage of 55.2, and a low voltage cutoff of 48 volts. And for a load on these inverters, I have a 30 amp double pole breaker in the middle, and I've got some 10-4 cable, some flexible cord here. Gonna run over to my clothes dryer, and that should put approximately a 5,500 watt load. So yeah, it will be interesting to see here how that works. All right, these inverter fans have gotten quite loud here. And we're pulling about 118 amps from our SOK battery rack here. And that is 5,664 watts. So I see on this inverter it's showing the load at 2.91 kilowatts. This one's showing 2.61 kilowatts. 2.94, not quite sure why that is. Maybe it's pulling some from the neutral lead, causing a slight imbalance. All right, so that was a pretty cool test. That clothes dryer ran for about an hour there. There were no issues at all with these inverters. I checked all the cabling, all the connection points. There was no heating issues or anything like that. These did get warm, warm as I would expect them. They weren't overly warm, but I do see why they have those spacing requirements now. You definitely need to allow some ventilation below for the hot air to blow out. These inverters do suck air in from the top and blow it out the bottom. It's kind of against what you would expect, but that is how they are built. Now, I will link to these inverters in the video description. However, it's increasingly difficult to get these MPP Solar inverters. I purchased mine from Watts 247, and it seems they are constantly on back order or pre-order or whatever you want to call it. So I'll also link out to Signature Solar. They produce a very similar inverter. It's pretty much identical, except they have a higher voltage MPPT charge controller, and they don't have the MC4 connectors on the bottom. Apparently those won't pass inspection if you need your system inspected. I think it has something to do with the MC4 not being a strain relief or something of that nature. Obviously, I did not talk about solar connections in this video. I think it's long enough the way it is. I have a previous video where I mentioned how to size up and connect solar panels. I may do a follow-up where I talk about it a little bit, but I don't have that immediately planned. Additionally, fusing. Ideally, there would be a fuse coming in before these bus bars. You saw I put 2 fuses after the bus bars. And those fuses after the bus bars are to protect the cabling, the 1/0 cable from overcurrent. Ideally, there would also be a large fuse on the 4/0 cable to protect that. However, I feel in this particular setup that is sufficiently protected between those 2 fuses I installed and the 4 circuit breakers on each battery. If I were to wire any more batteries, I probably would use a fuse on those 2 conductors. If you have any questions or comments, or is anything you want to see me test in this setup aside from the solar, please do let me know. I always read and reply to as many comments as I can. Hit that like button before you go, and thanks for watching.